Hello everyone, welcome to the video lecture series of the subject name VLSI Technology with the subject code KEC 053 as per AKTU syllabus scheme. This syllabus is the part of EC department. The EC students are studying this subject, and in this subject we are going to study the various steps which we are going to follow in the fabrication of any IC, right? So till now we have covered the photolithography process. With the help of photolithography process, we have created one window, right? So with the photolithography process, right? We have with the photolithography process, we have created one windows. Suppose two windows are created, we have created over there, and with the help of etching, we have removed the extra silicon. And the extra PR is also removed. So we have these windows, and over these windows, inside these windows, we have to diffuse some of the atoms, some of the impurities we are going to diffuse. Suppose we have this P-type substrate, right? And you know that in case of, if we have the P-type substrate, we can diffuse the N-type impurities so that we can have the NMOS transistors, right? So to form the NMOS transistor, we are going to diffuse the impurities of NMOS. Okay, so this impurity is added to this P-type substrate with the help of this diffusion process, and this is the topic of the discussion today, that how we can do the diffusion. So in the upcoming 2-3 lectures, we are going to study the models of diffusion in solids, fixed one-dimensional diffusion equation, diffusion of impurities in silicon and silicon dioxide, then diffusion equations, diffusion profiles, diffusion furnace, which are the diffusion furnace or reactors which we are going to use for the diffusion purpose. Then which are the sources which we can use for the diffusion. We can have the solid source, liquid source or gaseous source that can be used as a diffusion, right? Then what is ion implantation, the range theory and the ion implantation equipments, right? So this adding the impurities to the P-type substrate, or to convert the P-type properties into some another properties, into N-type properties, or to change the resistivity of P-type substrate, we are going to do diffusion and ion implantation. Okay, so these two processes are used. So these two processes, diffusion and ion implantation, are used to add these impurities in the substrate. We are going to see the difference between the two. So as per the introduction, diffusion and ion implantation are the two key processes to introduce the controlled amount of dopants into the semiconductor wafer, and this is done to alter the conductivity of the P-type substrate. Okay, so obviously we are going to change the conductivity here because we are adding some of the dopants. So the controlled amount of dopants are introduced with the help of this diffusion and ion implantation process. Okay, so what basically is the difference between these two? Here the first diagram is for the diffusion. So when you diffuse the gas dopant atoms, right, you can see here that the doping is extended in this direction, in lateral direction, as well as in vertical direction, right? But in case of ion implantation, the lateral extensions are less, right? We are with the help of ion implantation, we can have only the vertical diffusion. Vertical dopants will be introduced in the vertically inside the substrate. So this is more precise as compared to your diffusion. So depending upon the application, we can have diffusion and as well as the ion implantation. So the basic difference between these two processes is the diffusion is done at a very high temperature, whereas in case of ion implantation, it is carried out at certain low temperature. And the mask used here are the hard mask or SiO2 silicon dioxide. Here your simple PR photoresist material can be used as a mask. Okay, so this type of diffusion is known as isotropic. Isotropic, we have also studied in the last lecture also what is isotropic profiles. In case of isotropic profile, they will consider lateral as well as the vertical directions, right? So this adding of these impurities is done in all the direction, whereas in case of anisotropic profile, we are going to have the impurities in the vertical direction only. The lateral extensions are less, so that is why this is more preferred as compared to your diffusion. This cannot independently control the dopant concentration and junction depth. We can independently control the dopant concentration and junction depth. So what basically is a diffusion? So in the diffusion process, the dopant atoms are introduced from the gas phase by using the doped oxide sources, right? And the doping concentration decreases monotonically from the surface, and the in-depth distribution of the dopant is determined by mainly by the temperature and the diffusion time, right? So we know that this surface is in contact with the external gases, right? External dopant gases. So at above this surface, above this substrate surface, we have the maximum concentration, right? So when we are going to diffuse the impurities, it will be decreased from maximum to 0, right? So this diffusion is used to form the deep junctions such as N-tub in CMOS devices. Ion implantation is utilized to form the shallow junctions like source drain junction in case of MOSFETs. Okay, so this is the application where your ion implantation and diffusions are mainly used. So here you can see the diagram. We have the silicon wafer. Over that, silicon dioxide is formed with the help of oxidation process. Here we have created a window with the help of photolithography process, and the silicon dioxide is removed by etching. Now your dopant atoms are introduced and they are going to diffuse in the silicon substrate. Now what are the impurities which we can dope? We can dope boron. The boron is the most common p-type impurity in the silicon, right? So boron is the most important p-type impurity, we know that, and arsenic and phosphorus are used for the n-type dopants. So these three elements are highly soluble in silicon with the solubility that is approximate 5 into 10 raised to the power 20 atoms per centimeter cube in the diffusion temperature range, the diffusion which will be carried out at a temperature range of 800 to 1200 degrees C. These dopants can be introduced via several means, which include the solid sources Bn for boron, As2O3 for arsenic, and P2O5 for phosphorus. The liquid sources are BBr3, AsCl3 and PoCl3. This is for boron, arsenic, and this is for phosphorus. And in the gaseous form, we can have the B2H6 for boron, As2H3 for arsenic, and PH3 for phosphorus. This could be the sources for these dopants. And usually the gaseous sources is transported to the semiconductor surface by some inert gas, by using some inert gas like nitrogen, so that and this is then reduced at the surface. Now let us quickly check the theory of this diffusion. This diffusion is the process by which the impurities, we are going to add the impurities into the selected regions of semiconductor for the purpose of changing its electronic properties, right? At present, the diffusion is the basic process step used for the fabrication of both discrete devices as well as for the microcircuits, and both single and multiple diffusion steps can be used for this purpose. In silicon technology, this diffusion allows the formation of source and drain for the metal oxide, and secondly, it can be used for the designing of active areas in BJTs. It is extensively used for the ideal adapted to batch, for the batch process where your number of slices are used for the single operation, right? And unlike unlike this process, such as ion implantation, it does not produce crystal damage. Thus, high quality junctions can be achieved with the help of minimum leakage current and can be made easily by this process. So, the major drawback of the ion implantation is your crystal structure will be damaged, which we have to recover at the next step. So, how this diffusion mechanism is done? We have seen that in case of when we study about the crystal structure, we have seen that no crystal is perfect, right? Each crystal will have some deficiency, it will have some defect. Either it can be a point defect, right? We can have the point defect, vacancy defect, substitutional defect, which is also known as substitutional, right? Interstitial defect, right? So, which kind of defect is present in the crystal, in real crystal, that will help in the diffusion. Okay, so let us see the diffusion. Three type of diffusion mechanism we can have. So, first one is the substitutional diffusion, second one is the interstitial diffusion, and the third one is the interstitial diffusion. Okay. So, in what happens in substitution diffusion? In case of substitution diffusion, we must have some vacancy. Here we have the vacancy. This is the silicon atom and this is the dopant atom, right? This is the dopant atom. Now, this dopant atom will be shifted to this vacancy. Then this type of diffusion is known as the substitutional diffusion, right? Vacancy is already there and your impurity atom, dopant atom, is going to shift there. So, the limitation in this is adjacent to this dopant atom or impurity atom, there must be a vacancy. There must be a vacancy. Okay. So, the movement of dopant within the structure, if some vacancy is there adjacent to the dopant atom, this type of impurity is known as substitutional diffusion. Impurity moves along the vacancy in the lattice and the substitution is done for the silicon atom. Okay. Now, what happen in interstitial atom? In case of interstitial diffusion, this interstitial space is this space, the space which is present between the silicon atom, right? Depending upon the material which we are using, each structure will have the different interstitial space, right? For example, the diamond structure. If you recall the diamond structure, we have studied in first unit when we formed the crystals. So, in case of diamond, 35% is only occupied by the atoms, rest 65% is the interstitial space. It's the interstitial space. Okay. So, your impurity atom can easily move inside the interstitial space. That impurity has the plenty of space so that they can move from one place to another place. So, they can easily shift inside the interstitial place. So, this type of diffusion is much more faster than as compared to your substitutional diffusion. Okay, this requires more activation energy. And this requires less activation energy. Right? It is dependent on the vacancy, right? It is vacancy dependent. It is not dependent on vacancy, right? So, because it is vacancy dependent, this will be a slow diffusion, right? This will be a slow process and this will be fast. This will be faster as compared to your substitutional diffusion. Now, the third type of diffusion is known as the interstitial C diffusion. In case of interstitial C diffusion, we have the impurity which will be present in the interstitial site. It will push the silicon atom. The silicon atom will take place here. It will take place in the in interstitial site, and your dopant atom will take the place of this silicon. So this is the case of interstitial C diffusion. So this diffusion describes the process by which atoms move inside the crystal structure. This includes self-diffusion phenomena, but the goal is to study the diffusion of impurity atoms that are introduced to the lattice for the purpose of altering its electronic property. And in addition to that, concentration gradient and the temperature, crystal structure and defect concentration plays an important part in the diffusion. And wandering of an impurity in the lattice take place in a series of random jumps. These jumps occur in all three dimensions, and a flux of diffusing species results if there is a concentration gradient, right? There must be a concentration gradient. Above the substrate, we are going to have more concentration of dopants, and inside the substrate, we are going to have the less concentration. So there must be a concentration gradient. So let us quickly check the theory part. In case of interstitial diffusion, as shown in this figure, your impurities are present inside the interstitial space, right? So when an impurity atom moves through the crystal lattice by jumping from one interstitial site to next interstitial site, it is known as interstitial diffusion. This interstitial diffusion requires the jump motion occur from one interstitial site to another adjacent site. This process is relatively fast because the large number of vacant sites it will be present in the semiconductor. For example, diamond. Right, I have already told you that in case of diamond we have 60% free space. So your diffusion will be very much fast. Impurities such as lithium and sodium, they move inside the silicon by this mechanism. Next we have the substitutional diffusion. In case of substitutional diffusion, we have this dopant, and adjacent to that we have some vacancy. Your dopant will take place this vacancy, okay. So this is known as substitutional diffusion, I have already told. So an impurity atom walk through the crystal by jumping from one lattice site to next, thus substituting for the original host atom. So however, it is necessary that the adjacent site must be vacant and vacancies must be present to allow the substitutional diffusion. So this type of diffusion, as we have already mentioned, so it is vacancy dependent. Right, it is vacancy dependent. So substitution occur at much slower rate because it has to look for the vacancies than interstitial site, because the equilibrium concentration of vacancies is quite low. The diffusion of n-type impurities in gallium arsenide is done by this type of movement. Next is the interstitial C diffusion. It is the modified version of substitutional. The interstitial host atom can be removed by pushing substitutionally located impurity atom into the interstitial site. These impurities can now diffuse to the adjacent substitutional site and they will create a new self interstitials. Okay. So thus the interstitial position of the diffusion impurity atom is purely a transition state moving from one place to another place. This increases the concentration of vacant substitutional site over its equilibrium, so that the interstitial C diffusion is somewhat faster than this substitutional diffusion. All substitutional diffusions, they move by this mechanism, and the diffusion of boron and phosphorus is done by this process, interstitial C process. So this is the case of interstitial diffusion. Here we have the silicon, we have some atom, we have some dopant. So silicon, either it will push the dopant atom and dopant atom will come here, or we can have the reverse case also. Dopant atom is present in the interstitial space and it will push the silicon. Silicon will go in this space and this atom will take the place of silicon. So we can have the both the cases. Next, we can have the interstitial substitutional diffusion. In this case, atom occupies substitutional as well as the interstitial size. However, they only move at a significant rate when in the interstitial site is used. The dissociative mechanism by which the substitutional impurity atom can become an interstitial by leaving behind a vacancy. It can be controlled. It can be the controlling factor for this purpose, and as a result the effective diffusion is a function of dislocation rate, and it depends on both impurity concentration as well as the crystal quality, because your crystal quality will tell you how much vacancies are there. And copper and nickel moves in silicon by this interstitial substitutional mechanism, and zinc, cadmium and copper in gallium arsenide. When we diffuse these impurities in gallium arsenide substrate, this is also done by interstitial substitutional diffusion. So here we can see in the diagram that the diffusion is dissociative mechanism. This is done for the copper and nickel, and in case of gold and platinum we have the kick mechanism. Okay, so it is known as kick out mechanism. Generally, the question is asked in the exam that which type of diffusion, how the diffusion takes place in gold or in platinum. Okay, so under this we have to explain this diffusion process. An alternative path for this interstitial diffusion is the kick out mechanism. Here, a rapidly moving interstitial diffusers can move into a substitutional site by displacing an atom which is already in a place, which results in the formation of self-interstitial sites. The behavior of gold and platinum in silicon has been described by this process, that is by kick out mechanism. Okay. So always keep in mind whenever your gold and platinum diffusion is asked, how this diffusion of gold and platinum is done, we have to explain this kick out mechanism. Now, how this diffusion can be explained with the help of mathematical modeling. This is done by Fick's law. The diffusion of dopant in silicon is modeled by a simple diffusion theory which is described by the Fick's law. Fick's law states that flux of dopant atoms at any point is assumed to be proportional to the gradient of the dopant concentration at that point. The proportionality constant is the diffusion constant represented by D. This is assumed to be a constant for a given dopant species at a given temperature. Actually, D is not the constant, but it is dependent on the dopant concentration. Now, what this Fick's law we can write in terms of equation: the variation of dopant concentration with distance into the semiconductor is known as the dopant profile. Now, consider the one-dimensional case in which we consider only the dopant concentration varied in x direction. Suppose we have this. Suppose we have this profile. Okay, here we have. Okay, we have this kind of profile. Here we have the P1 flux, P2, and it is moving in this direction. This is the dx distance. Okay. So it is given by the dopant diffusion is governed by the Fick's law, diffusion law. It states that J is equal to minus D del C xt by dx. Okay, we can also write it as this J is equal to minus d dn by dx. Okay, here it is the concentration. Okay, concentration at certain distance at certain time. Okay, so this is the dx, this is the dx for which your diffusion is we are going to done. Okay, so according to first law, the diffusion, the transfer of solute atoms per unit area is given by the dimensional flow and can be described by the following equations. So and this minus sign indicates that your diffusion is from higher concentration to lower concentration. So that is why we have this minus sign. This J, we can also write it as minus d. All these things are J. J is the number of atoms crossing area per unit. D is the diffusion coefficient or diffusivity. Okay. C is the concentration of solute, and this, it is the matter transport is down the concentration gradient, right. This minus sign is because we are going from higher concentration to lower concentration. Okay, that is why we have the minus sign. So we have seen this equation, J is equal to minus d del C, that is the concentration divided by distance. J is the rate of transfer of solute per unit area or diffusion flux. C is the concentration of solute, which is the function of x and T, temperature only. X is the coordinate, x is in the direction of solute. T is the diffusion time, D is the diffusivity or the diffusion constant. Now, what is there is some limitation of this law, although it describes the diffusion process accurately, but has no convenient measure to check the current density of the impurity. So, the second law is developed to describe the concept with more readily measurable, it will give you more readily measurable quantities. So, the second law, as per the second law of conservation of matter, the change of solute concentration with time, it must be same as the local decrease of the diffusion flux, that is the change in the flux in the absence of source or a sink, that is given by, suppose we have this substrate, here we have the flux and flux 2 J1 and J2, this is the distance I have already shown in the previous slide also, right. So, we can write it as the concentration at certain distance with respect to time, it will be written as minus djxt divided by dx. Then we can substitute this previous equation, in equation 2. In equation 2 we are going to have this equation, okay, and further we can write this equation as, we can solve this so that we can have this equation, that your concentration gradient, it will be equal to d del square C at the coordinates of xt, that is your distance and time, divided by dx square. The analytic solution for this fixed law is when the value of this d, it can be infinite or finite, okay. So, all these things comes under this solution. So, when the total diffusion source concentration is fixed or it is not fixed, we can have the constant diffusivity. So, the solution for this constant diffusivity is done by three varieties: the constant surface concentration, constant total dopants, and sheet resistance of diffused layers. So, here is the first solution to this fixed law with the constant diffusivity. In case of constant diffusivity or infinite source of diffusion, it is also known as pre-deposition process. So, to understand this process, we have the wafer, and your gases are flowing in a continuous way, right? We have the infinite source, but you know that your substrate must have some capacity to absorb that dopants. So, right. So, the diffusion is limited by that point, that how much dopants your substrate can absorb. So, in case of infinite source diffusion, it requires a constant concentration of diffusing atoms, that is the flux of impurities continuously arrives at the surface of the substrate such that the concentration gradient of the impurity remain constant at the surface of the substrate, right. Suppose this thing is kept inside the chamber, okay, this thing is kept inside the chamber, we have some gas inlet, okay, some gas inlet is there, and your gases are continuously flowing, right. So, the concentration over this will remain constant. So, this corresponds to the process, it is known as pre-deposition process. So, a layer of gases will be deposited over here. With the initial conditions t is equal to 0, at time is equal to 0, this concentration is given by C x 0, at distance x it is 0, and the boundary condition concentration at x0 with some time t, it is given by Cs, and C at some distance infinite at certain time we have 0, it will be decreased, right. So, this solution is given by this equation. Let us check how this equation is calculated. Okay, so we have the flux P1 minus flux P2 multiplied by area. This will be equal to your rate of, it is given as rate of accumulation of dopant atoms in between P1 and P2. Okay, so we can write it as, here in the previous slides I have mentioned in the term of concentration, that is C. Here I am denoting just by N by T into area into dx. Dx is the distance between F1 and P1 and P2. Okay, it will be right. There will be some concentration difference, there will be some flux difference at 2 points. So, this we can write it as dN by dt, this can be cancelled. We are going to have minus j x plus dx minus jx divided by dx. Okay. So, dN by dt, that is equal to minus del j by dx, where dx is equal to 0. At dx at x equal to 0, we are going to have this dN by dt will be equal to minus dj flux divided by distance. Okay. So, substitute the value of j, this j from the first equation, from equation 1, we are going to have dN by dt, that will be equal to d by dx this is the Fick's second law. Okay. So, this is the Fick's second law, and then dN by dt, d by dx, dN by del by concentration with respect to X. This equation is valid for all the dilutes. Okay, this equation is valid for all the dilutes. Now here we can have whether your n is constant or infinite. First case we are taking, it is this, the value of D is infinite, right? We have the infinite source. We are taking here the value is infinite source. So the doping concentration in crystal that is n, it can be written as n x at time, it is given by n naught error function complement x divided by 2 under root of dt, okay, where d is the diffusion coefficient and t is the time, okay, and this error function complement is 1 minus error function of some x, and this error function x, it is written as 2 under root of 2 divided by under root of pi integral of 0 to infinity exponential of minus z square dz, okay. So if you put these values in this equation, we are going to have n x at time t n naught error function complement x divided by 2 under root of dt, and we are going to have the profile like this. Your concentration will remain same because it is maximum concentration will be your, it is given by the maximum solubility limit, of the substrate, right. So it will remain same, and depending upon the time you are going to change the diffusion. Okay, so from so these equations are calculated from here. So this is the explanation of these equations. So next is the constant total dopant. If your source is now limited, right? So once all the gases are present inside the chamber, switch off that gases. Now we have the limited source. Okay, that process is known as the drive-in. This process is known as the drive-in process. So here your equations will be integral of 0 to C n, we have seen in the previous equation, that is equal to Qt, that is equal to dose, that how much dose we are going to diffuse inside the dopant. It will be calculated as this concentration will be Qt dose divided by pi dt exponential of minus x square divided by 4 dt. By setting the value of x is equal to 0, we are going to have the surface concentration Cs is equal to at distance 0 and time t Qt divided by under root of pi dt. This is known as the diffusion length. That under root dt factor is known as the diffusion length. So in the previous case, when we have the pre-diffusion, we have the error function, complement error function graph. But in case of this drive-in process, we are going to have this Gaussian distribution. Okay, we are going to have the Gaussian distribution. This will be the graphs for this Gaussian distribution and pre-distribution. Here in case of pre-distribution, it starts from the same point, right? It depends on the maximum solubility limit. Right. So here we can see some changes. So depending upon the time, depending upon the temperature, there will be some changes in the graph in case of drive-in process. Okay, so next is the distribution of when we have the constant dopants. So when we have the constant dopants, now your impurity concentration is constant, right? We have the chamber we have the chamber, this chamber, and here your gas concentration is now constant, no gas, no extra gas flow is there, okay, no extra gas flow is there, okay. So inside this we have the substrate, p-type substrate, right. We are going to diffuse some of the dopants, right. Over here we are going to diffuse the dopants, okay. So here we have the now limited source, we have this limited source. So obviously we have maximum concentration here, more concentration will be at this point, and we are going to have less concentration at this point, right. So when we go deep down the substrate, your concentration also decreases, right. So when we go inside the substrate, your concentration will be decreased. So here we can see that when we have more close to the substrate, this is your case 1, more close to the substrate, we have good concentration. When we move down the substrate, your concentration is decreased to N02. When we move more further inside the substrate, we have the concentration N03. So today we are going to stop here, and finally we can conclude that the doping, the diffusion process is not a single process, it is a two-way process. First one is we have the pre-deposition, a layer of gases will be deposited there, and that layer of gases will be diffused inside the surface with during the drive-in process. So we have learned about the diffusion, how the diffusion is done, how it is dependent on the crystal structure, and what is the basic difference between the ion implantation. So in the upcoming slide, we are going to see the reactors, which are the reactors which we are going to use, and how the ion implantation is done. Thank you so much.